Greetings, chemistry class. Today's video has a companion notes sheet that was already part of your packet that'll be titled Chemistry 11.9 Math Examples. So I'll be working from that and from the book starting on page 301. So these problems are going to be a little more challenging than other questions earlier in the chapter because they're going to use information from this chapter as well as some old information, including some dimensional analysis. So I'll ask you, as always, just try to do your best with what you can here. The first problems are called molecular mass problems. So the issue with these is, as the notes explain, you have to first have all of the pressures be dry pressures. Those are the ones a few days ago we subtracted the number in the back of the book from that table. And they have to be at STP. To be at STP, we're going to have a thing like this, the combined gas law equation, the PV over T, PV over T equation to use a good bit. So I'm on example, I told you the wrong page number, I was fibbing. We'll end up on that page. We're starting on 297. So 297, there's an example 1113 that says find the molecular mass, which is an old thing we did a few chapters ago, and the molar mass, which is back a few chapters. If there's 600 milliliters of the gas at 30 and 630 torr, and there's a mass of 0.600, we do not care about the mass of 0.600 yet. Okay, we're going to start off with this question just doing the equation that we've been using. So we're going to take the 630 is a pressure, because we're doing PVs on top of T's. So 630 is a pressure. No, wait. Yeah, 630 is a pressure, 630 torr. The volume is 600, because milliliters, as always, measure volume. The temperature isn't going to be 30, it's going to be 303 by the time we add 273. We can't do any kind of math with this stuff permanently to do the molar mass question because it's not at STP. We're going to have to use this equation to get to STP. So if we go to STP, standard pressure is 760. Instead of 630 torr, 760 is our standard. Instead of 303 Kelvin, 273 is our standard. We don't know that. So as always, top number goes down, bottom number goes up. Punchy, punchy, punchy. Calculator's going to give you a 448 milliliters. If you can't do that, don't try this homework yet. Go back a few videos, watch the combined gas law video, work those problems from earlier in the chapter. If you can't do this chapter problems, this is not the video for you to be watching. You've got to work on the earlier chapter. Then we're back a few chapters. You might remember back a few chapters we had problems where when we had grams, which we do, we have 0.600 grams in the paragraph. We have 448 milliliters from our math. We used to do some dimensional analysis where we always, if we had grams and milliliters, we always put grams on top of milliliters. And what they're asking you to do is figure out how many grams there are in a mole. So milliliters needs to go. Milliliters are easier changed to liters than anything. There are 1,000 milliliters in a liter. And we can get from liters to moles. Liters getting to moles is going to be familiar when I say it in a minute. If you're a super chemistry genius, you already are going to recall instantly 1 mole was 22.4 liters. We did a whole chapter where we used 22.4 liters constantly. 1 mole is always 22.4 liters, and I shouldn't have crossed out moles, got a little carried away when I was crossing off. So if we do the math on this, we are going to churn out a 30.0 grams. That is the molar mass. The molecular mass is also 30.0, but AMUs. You might remember doing that a few chapters ago. The molar and molecular masses, it's the same numbers, just the molecular mass is for the molecule, tiny, 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 measured in AMUs. The molar mass is more of a manageable amount in the real world here that you could see. That was always measured in grams. Next example up is 14. 14, they add on a small bit at the beginning, but otherwise they do the same thing. So if you didn't quite get that, we'll redo the whole process on this one with an add at the beginning. So on 14, the key difference on 14 is when you read it, blah, 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 right in the middle, collected over water, which means it's a wet pressure, which means we have to remember the lesson from the Dalton's Law of partial pressures. Take 720 and subtract a number from the table in the back of the book, which happens to be 31.8. And that gives me a 688.2. That's our first move, is make a new pressure, a dry pressure, by that subtraction. So 720 is not going into the equation. 720 is out, subtracting, we get 688.2 is in, and we need to use that. So 688.2 is a pressure. And again, 31.8 from the table in the back, as a couple days ago we also did. So 688.2 lives there. The paragraph has a volume of 450. Paragraph has a 30 Celsius, is a 303. And as we did a second ago, we just need to get to STP. So it's 760 again, it's mystery again, it's 273 again, it's the same zigzag again. We get 367 milliliters if you do that right. Somewhere in the question there had to have been grams, just like here they gave us grams. They're going to have to give us grams again, so we'll look that up. And I have a 0.515. When we do dimensional analysis with this, it's always grams on the top, and it's always a milliliter on the bottom, unless you get lucky and it's liters. If you got liters, you wouldn't have to have done this conversion. If they gave you liters, we'd be maybe a step farther down the road. But we're trying to get rid of milliliters to get liters. 1,000 milliliters is a liter. Then we need to get rid of liters to make moles. It's still a 1, it's still a 22.4. We're going to punch in, multiply all the top numbers, divide by's for anything on the bottom, and we're getting 31.4 twice, grams for the one, AMUs for the other. Second group of problems, I'm turning the page to the next page, and in the book I've worked my way up to 299 spilling into 300. Density problems, we need to eventually get to a point where for a density we're dividing a mass by a volume. But the problem is the stuff isn't right the way it's given to you. So the first thing we're going to have to do is work at STP and figure out what's going on at STP with a dimensional analysis move. And then we're going to have to do a conversion. So they're going to tell you something like SO2. So what you're going to have to do is a dimensional analysis thing based on SO2, always with grams. Use your periodic table. S is 32-ish, 32.1. O is 16. So 32 needs to add 2 of the 16s. Add that all up, and it's going to be a 64.1. The 0.1, the sulfur has a 0.1 when you round it. I think the table is 32.06. But we're going to round the O up to a 1 because the 6 makes us do that. What we're looking to do here is make a density where it's not grams per mole, but densities are things like grams per liter. So moles are going out, liters coming in. 1 mole, as it was in the other column, is 22.4 liters. And so this is giving me a 2.86 grams per liter. Second, what we're going to do is convert 1 liter at STP, always 1. We're always going to do, stick the letters over there, that helps you slot them. Take a volume of 1 liter, always take 1 liter. Take a 760 pressure, standard. Take a 273 temperature, that's standard. And we're going to do a transformation here to the numbers from the problem that didn't matter till now. The problem's talking about 640 torr. If the problem didn't have torr, but it had like some other unit, we wouldn't have used the 760. Okay, 640 torr, maybe do 760. But something other than torr, we have numbers from the quiz we memorize. They're telling me a temperature 30 again, so 303 again. So figure out what that is by this goes down, this comes up, and we're hoping for 1.32 liters. And then it's just a division to finish. Take the gram number from a minute ago, take the liter number from less than a minute ago, and we're going to just take the 2.86 divided by the 1.32 and hit it, and it's going to say 2.17 grams per liter. The last group is stoichiometries. Stoichiometry we devoted a full chapter to back a ways. So we're going to look to use dimensional analysis the way we did back a ways, using the coefficients on the equation again, those kind of things. But there's also going to be a PV over T kind of move. So some of the problems you'll do the PV over T first. Sometimes you'll do the PV over T last. The ruling is, and it's on the notes here, if they give you a weird temperature and pressure to start, you do the PV over T equation first. But if they ask you to do an answer that's at a goofy temperature and pressure, you'll do the PV over T last. So I'm on 1116 now up to 301. So they give you an equation and then a book at the top, and they use the unfortunate word unbalanced. Not everything's unbalanced, but this one is. So when we balanced equations, we'd have to check the K's, which are good, the CL's are good. We always save the O's for later. The O's are bad. Odd numbers are usually ruinous. So to make that an even number, take 2 of them. Now there's 6 oxygens. This, if you did a 3, is now 6 oxygens. But the K's and CL's, the 2 just imbalanced those. So now we need a 2 to fix that. Hope in the homework they give you balanced equations, but one never knows. So now we're going to do an old style, let's see, an old style dimensional analysis problem. They want us to calculate the volume of liters at 35 and at 630. So they want an answer not using the standard numbers. So we're going to save the PV over T for later. What we need to do is dimensional analysis to answer the question that they're asking us. So they want us to do an oxygen amount in liters. So what I'm going to have to do is change grams of the known and figure out moles of known. We had a 3-step plan in that chapter. Step 1 was find moles of known. So if I go 1 is the number for moles always. The number for grams is coming from the periodic table. Add up K, add up CL is in the 35s, add up O, I think it is. Add up O is 16 times 3. Periodic table, add. This is going to get you 122.6. Then we had to translate from the moles of the known to the moles of the unknown, which in this question they want potassium chlorate. No, that's a lie. We had potassium chlorate. They want oxygen. So we need to get to moles of oxygen. Coefficient for oxygen is a 3. Coefficient for the KClO3 is a 2. And then we still have one more move to go because they didn't ask us moles. They asked us liters. So here's our friend again, the 22.4 with a 1. So we have to remember and be able to still do all that stuff from a couple chapters back to get 2.47 liters, which would be at STP. When you're doing this old stuff, that only is true at STP. You want to celebrate and feel like you're done, but all that did is feed us a number to do the new math. The 2.74 liters is a volume at STP, meaning we're at 760 compared to, they wanted us to be at 630 torr. We are at 273, but they wish us to change to 308 because 35 adds 273. Don't know that, so we go down, we go up, zappity zap zap zap. 3.73 liters of O2 should come out, and then you should have much rejoicing because you earned that one. That was a lot of work. The next example is in reverse order, essentially the same thing. They start off and they give you 4.13 liters of oxygen at a weird temperature. So the 4.13 is weird temperature, weird pressure, so we're going to do that PV over T first. So for this, they're giving us 680 torr. And we need to get that to be 760 for this to be allowable. We have a 4.13. We're going to make a new volume, and that new volume is going to feed in here to get us started. There is a 303 that's based on the 30 they gave us, but that has to translate to 273. Down, up, math. 3.33 liters is created to take here. Beauty of the videos, you might have to watch that again. If this were in class, I'm sure I'd be talking again, but you can just rewind that and watch it again if I lost you. We don't want liters. We need to turn liters into moles. Step one, find the moles of the known. 22.4 liters, always for 1 mole. Then we need the moles of the known to go away for moles of something we don't know. So moles of O2, moles of O2, bye-bye. Moles of something new we want, which is potassium chlorate, that is the KClO3. KClO3 is still a 2. The O2 is still a 3. And then we're actually done, hooray. They stopped one step short there. They asked us for moles, and we have moles, and we're done. We go 0.0, which doesn't count as toward our 3 digits, 991 moles, KClO3, boom. In another question somewhere out in the world of chemistry book writing, they might want you to get from moles even farther to grams or something like that. So if they did that, we'd have had 1 mole, and we would have had to use the periodic table here to, this would have come back into play, because we already did that for the earlier question. We'd have had to do the gram number here to get back to grams. If they wanted to be cruel people, they might have even gone to milligrams, or might have started you off with milliliters or some other ridiculous thing, and that could have even expanded that a step. But we hope they don't do that. That's it.